Alright, so now we can actually start building our calculator. So the file I'm in here is the file, the Jupyter notebook that we finished up our last project with. It hasn't been changed at all, it's the exact same file. So if you haven't finished or worked your way through that project, I'd suggest that's probably a better place to start. But assuming you have, this is the file you would have finished that project with. So we need to make a couple of tweaks to this file before we even think about calculating our deflection. The first thing I want to do is actually modify my title here. So it's a bending moment, shear force, and we'll say and deflection calculator. Okay, so let me see. Yeah, we'll leave that as it is for now. Now the note here says it's for statically determinate beams only. This full code is for statically determinate beams only, but specifically the calculation of deflection can be deployed, as we said previously, on statically indeterminate beams. All it requires is that you have the bending moment at each position along your beam. But that's all we need to say for that for now. So let's come on down and start making some edits. So the very first thing that I want to do is I want to build this code initially around our example that we used in Macaulay's method, in our discussion of Macaulay's method. So if we go back over there, it's this beam here. So this was the example we ended Macaulay's method with. Now we noticed that this particular beam has a cantilever overhang on the left hand side and on the right hand side. Now our original shear force and bending moment code could take that into account, and our deflection calculator is also going to have to take that into account. So let's just start off by reflecting the loading and the arrangement of this beam over in our calculator. So we can start working through that bit by bit. Now the span for that beam was actually 16 meters. We had 3 meters to the left support. Let's check that. Let me see if I come over here. We've got 3 meters into the left support. Now B is the distance into the right hand support, and that's going to be, let's see, 5, 9, 10, 11, 12, 13 meters. Okay, so we can change that. Well, that's already 13, so that's fine. And now we can start representing our loading. So that particular beam had 2 point loads. So it had a point load, let me see if I come back out so I can switch between tabs. It had a point load of 100 kilonewtons at 4, 5, 6, 7, 8, 9, 10, 11 meters, and a point load of 75 kilonewtons in the negative Y direction all the way over on the right hand end at 16 meters. So let's get those in there first. Alright, so we said with 1 at 11, now its horizontal component was 0 and its vertical component was going to be negative 100. Now we had a second point load, which we can just include straight away like this, and so that was located at 16 meters, horizontal component again of 0 and a vertical component of negative 75. So that's our point loads taken care of. Let's just break those onto a new line. Now we can deal with the point moments. It had a moment, again, let's switch back across. It had a moment at position 0, and that was a counterclockwise of 60 kilonewton meters, which would be a negative 60 for us. So let's jump in here and say at position 0 it has a negative 60 for point moments. Now this particular beam doesn't have any linear loads. Those are linearly varying distributed loads, but it does have distributed loads. So let's just change this to be distributed loads. Now the distributed loads, we have to pass in the starting point, the ending point, and the magnitude. So it starts at 5 meters, it ends at 9 meters, and it has a magnitude of a 50 in the negative Y direction. So that's a negative 50. So that's how we define a distributed load. Again, let's jump over. Again, it starts at 5, it ends at 9 and has a magnitude of 50, and it acts in the downwards Y direction. So that's a negative 50. Okay, so that pretty much is all we need to specify, and for any beam, any structure we're going to analyze this code, that's all we're going to want to specify. So let's run the code now and just make sure it runs from start to finish. Okay, excellent. So we have our reactions, we have our shear force diagram, and we have our bending moment diagram. And of course, it's the values that make up this bending moment diagram that we're going to want to use in our deflection calculation. So if I come on down, you can see I've already sort of pre-prepared the ground here a little bit. I've just set a new title, deflection calculation. we're going to have our deflection related user inputs in here. We'll have some constants and initializations in here, and where the bulk of the work in this particular video is going to be, it's not going to be a lot of work, but the majority of our efforts are going to be deployed in here, where we actually define a function to implement our numerical integration. Now, before I jump down here, there is one thing I want to do back at the top here. You can see when it came to working out all our range of x values, the approach we took previously was to specify the number of divisions, the number of divisions we would break our beam up into. Now, what that means is that we wouldn't necessarily have a value of x that coincided with, let's say, the right-hand support. And we know that we're going to need to check the deflection at the end of this. We're going to have to check the deflection at the right-hand support, specifically at the right-hand support. So we want to make sure that we have a value of x and therefore a value of moment and therefore a value of deflection at specifically the location of the right-hand support. And so rather than specifying the number of divisions, I'm going to specify the division length, or the delta here, directly. And that's going to ensure that I have a value that lies specifically on that support. So in other words, if I get rid of this and instead I say delta is going to be equal to, let's just get rid of this and say 0.005, right? So 0.005 meters. And again, you're going to want to tweak this and potentially change this for your structure. But for now, we'll say that that's sufficient. And what that means is I'm going to have a value of x and therefore moment and therefore deflection at precisely, if I jump back over to our image here, I'm going to have a value at precisely this location here, B, which was 13 meters in, right? Because obviously this 0.005 divides evenly into 13, right? So that's the first little tweak, nothing major, just a minor modification. So now we can scroll on down and actually start writing some more relevant code, or code relevant to our calculation of deflection. So the first thing I'm going to do is I'm going to specify an initial rotation. Remember, we had to specify what was our initial guess for the rotation. Now, I've been playing around with this, obviously, so I'm going to put in a reasonably close value of the deflection, or rather the initial rotation, I should say. So let's start at minus 0.0021. Now remember, your code should navigate its way to the right value, so in theory it shouldn't really matter what initial value you put in. So we're going to start with minus 0.0021. So that's our initial value. But remember, if that's not the correct value, we're going to want to change it slightly and then run the test, run the calculation for deflection and then run the test again. So how much do we want to change it by every time we iterate and every time we test for the initial value? So I'm going to set a delta rotation. This is the amount by which we're changing our initial guess every time we do our test. And this is going to be some number that's going to be smaller than this. Okay, so I'm going to go for a really small number. Now, the smaller you make this number, the closer that your guessed value will get to the theoretical correct or perfect value. So you can think about this as the amount of fine grain control you have over that initial rotation. So I'm going to go for 0.000005. Okay, so that just means I'm going to get a value of deflection that's going to be very, very close ultimately to the actual correct value. And so if I was to make that, let's say 0.0005, I would get close to the correct value of initial rotation through my iterative process, but my final deflection wouldn't agree as closely with the analytical solution. So again, play around with this, right? Let's get the code written first, and then we can play around with all these different parameters. So they're the first two bits of info I want in. Next, I want a Young's modulus, because we can't calculate deflection without factoring in what type of material we're dealing with. So I'm going to go for my standard value here of 200 by 10 to the power of 6 newtons per meter squared, and then a second moment of area. So we can put in a value, or we can actually calculate a value on the fly. So I'm going to assume I'm dealing with something that is a beam that is 200 millimeters wide by 500 millimeters deep. So that's going to be B times D cubed, 0.5, let me see, 0.5 BD cubed over 12, and that's going to be my second moment of area. So that's all of the input information I need. Let's just pad this out with some notes and some titles, just so it makes a little bit more sense to us when we come back at some point in the future. Okay, great. So we have the initial user input defined. Now, when you finish this code, you might decide that you want to take all of this information and you want to put it back up at the top of your file, and so you can, you put all of the user input information at the top here. That would probably make more sense if I'm honest, but for the purposes of writing this, for explaining it, makes more sense to keep it down here. Right, now next thing we want is some initializations and some constants, right? So what I want to do first of all is define M here, and this is going to be the array of values, the array of bending moment values that we calculated or that we used to draw, if you like, this bending moment diagram. So I'm going to just take the sum of all of the bending moment values. Now these were calculated previously. This is a container of bending moment values that we've already got from the previous project, from the code above, and I'm just going to take the negative of that. Next, I'm going to define delta x. This is just going to be the difference in x values. You can either specify, well, I mean, we already specified it actually. We specified it, where is it? We specified it here, delta, but so I can either say delta x equals delta, or I'm going to stick with what I wrote originally, which was the first value of x or the second value of x minus the first value of x. Either or works. Next, I don't want to write e multiplied by I every time, so I'm going to define a new variable called ei, flexural rigidity. That's going to be e multiplied by I, just a little bit of personal preference. I'm going to define an initial deflection, right? An initial deflection. This is going to be the deflection at the left-hand support. Our calculation, our algorithm is always going to start at the left-hand support, even if there's an overhang, cantilever overhang to the left of that left support. We'll deal with that in a couple of videos, but we're always starting at the left support and integrating to the right. Right, so we're going to let that equal to 0. Now, because our left support and our right support don't necessarily correspond with the left edge and the right edge of the beam, again, because we could have cantilevers on each end, I'm going to want to have access to the index for any value, i.e. any moment value or any x value. I want to have the index or the location or the address that corresponds to the value at support A and the value at support B. So that might make more sense when I actually type it out here, right? So let me define a variable called support index A, right? Now that's going to equal, imagine my container of x values, and let's say I want to know what is the index of the value of x that is equal to A, right? Now I'm building this up. It doesn't make that's not valid code, right? But we'll build it up. So I'm going to use from NumPy handy little function called where, and what that's and I'm passing in x equal to A, and what that's basically saying is NumPy is running through all of the values of x, right? It's running through them all, and it's going to extract or take out the index, right, the location or the address of the value within x that is equal to A, right? Simple as that. And we're going to index off the number that comes back from that array. And then I'm going to call item on the end, because ultimately what do I want? I literally want a number. Let's run this and see what it gives me, right? And I'll elaborate a little bit more. Okay, so we have, what do we have an issue with? I didn't run this. Let's run this and then run this. So what's that saying? Support index A is equal to 1875. All that means is the value in here, right? The value within x that happens to be equal to A is the 1875th value in x, right? So it just gives me the location or the address within this big array of the value that is equal to A, where A was equal to 3 meters. All right, so that's all that is. We want to do the exact same thing for support at B. I want to find the index. Support index, let's call this B, and that's going to be np.where x is equal to B, and it's the exact same. The rest of it's the exact same. Okay, so let's go ahead and put some comments around all of this. Okay, great. So we have our initial constants all established. Now we can get into the meat of this, which is actually defining this function. So let's start off. We're going to define a function. We're going to call it calc deflection, right? So calc deflection, Okay, what is this function going to take? Well, it's going to take in all of the values at bending moment. It's going to take in the flexural rigidity. It's going to take in delta x, okay, the x increment. It's going to take in the initial value, some initial value of rotation, and it's going to take in an initial deflection, V0. So these are all the bits of information that this function is going to need in order to spit out at the other end the value of displacement for every position along the beam. Okay, so let's think about this then. The first thing that I'm going to do is I want to write my variable names such that they make a little bit more sense to me. And so what I need to do is I'm going to define, instead of using theta 0 and V0, I'm going to define theta underscore IM1, right? This is obviously going to represent theta I minus 1. So that's going to initially be set to be whatever value got passed in for theta 0. And then I'm going to want to define V underscore IM1 for I minus 1. And that's going to be set equal to whatever value was passed in for V0. Now, this is completely optional. You don't have to do this, but to keep the logic straight in your mind as you're working your way through writing this function, or at least for me anyway, I find it's very helpful to have variable names when I'm doing some kind of a stepping function like this. Variable names that actually make some kind of sense are very helpful. So let's just put in a couple of notes. So the next thing I'm going to do is initialize some containers to hold my rotation and deflection values, because think about what's about to happen here. We're about to write a loop that's going to step through all of these moment values, and based on what we described in the previous lecture, the theory-based lecture, we're going to generate a value of rotation for every position along the beam. And I'd like a bucket that I can hold or contain or store those values of rotation in. So let's define rotation as being equal to a numpy array of zeros, and it's going to have a length that is going to be equal to x, where x was all of the x values, right? So we just want to get an array that's the exact same length as our array of x coordinates. We're just going to fill it with zeros, and then we're going to override those zeros with the actual values we calculate in due course. So now that we've done that, well, what we can do now is we can say we can manually assign the value in here, and this is where our support index A comes in. Let me write this out, not explain it, right? So we're manually assigning into the rotation array at this location, support index A, the location that corresponds to support A. We're manually saying that that is going to equal, that's going to equal theta I minus 1, right? So we're stepping in and we're saying, okay, well, I already know whatever the initial value of rotation is at support A, because I'm assuming that. As far as this function is concerned, that's a value that just gets passed in. Now, in the wider context, we need to guess that value and then subsequently check if it was correct. But for the purposes of this function, all it knows about is we gave it some value of theta 1, or theta 0, I should say. And so we're here redefining the name, we're just renaming it. But in this line here, we're manually stepping into this bucket of zeros that we just established, okay, in this line, and we're manually stepping in and we're saying, well, let's override the 0 that corresponds to support A, the value at support A, with whatever the initial value was. That's all that's happening here. And the reason we have to do this, the reason we can't just say rotation at position 0 is because the rotation at position 0 is going to be some rotation down here at the left tip of the beam, whereas we're starting over here, and that's why we needed to work out what was the address or the location for all values that correspond to this location, not this location down here, but the location of support A, because we're starting here and we're integrating to the right. Then we'll come back at the end and we'll integrate to the left, but don't worry about that for now. So now that we've done that, let's do the exact same thing for our displacement values. So we'll say, well, let's call it deflection. We'll say deflection is going to equal, and I can copy all of that and drop it in there. Okay, and now we're essentially assigning in the same way we did for rotation. We're saying deflection at, don't forget to fix this. That would lead to headaches down the road. That should be support index A. Now we're saying the value within the deflection array of at support index A is going to equal whatever the initial value was that was passed in. Let's say V I minus 1. Excellent. All right, so now we're ready to start looping through each of our values and building those trapezoidal rule equations. So let's keep things ordered here and just put a heading in. And we'll start off down here with another heading. Let's start this, let's build this loop. So we'll say for m in the values, all the values of m, remember they all got passed in here. These were just the values, they were ultimately these values that got passed into the function. But I don't want all of them. Remember, I said we're starting at support A, so I only want the values of bending moment that correspond to, let me jump over here, that correspond to this location and to the right. Right, so I don't want all of them starting down here and to the right. I want all of the bending moment values starting at support A and going to the right. So in other words, I have to call this loop over. It has to iterate over values of m, not all of them, but only the ones from support index A to the end. Now I want to add a little color to this, and I'm going to say I'm going to add an iterator here. I do this, if you've watched any of my coding tutorials, you've seen me do this a million times now. So it's always handy to have a little iterator here, a little counter that starts at 0 and increments up by +1 every time we go through the loop. So we're just going to add that in there. I even add that in if I don't even think I need it. It's just handy to have. We do actually need it in this case though. So now that we're looping through all of the values of bending moment from support A over to the right end of the beam, we need to now define the actual index. Remember, it's not going to be I. I starts at 0 here, right? It's going to actually be, I plus whatever the starting index was, which was, of course, support index A. So, having this potential overhang to the left, well, mainly the overhang to the left, it introduces a little bit of extra complexity, but it's nothing too hectic. So this is just now our index that keeps track of the correct address or the correct location corresponding to each position along the beam. So now we can actually do the integration. So if we're greater than 0, so we don't do this when I is equal to 0 when we come through the first iteration of the loop. Remember, we need the first two values of rotation, or rather we need the first two values of m at 0 and m at 1 in order to calculate theta at 1, right? So we only come in here if we're past that first value and we're on the second value. In other words, if I is greater than 0. And what are we going to do? Well, let's start off by defining m. Again, this is optional, but it's handy to keep it clear in your mind. Let's define the value of moment at I minus 1, and that's going to be equal to the value at moment at this index that we've just defined, ind minus 1. That's why we defined ind. Now let's define the value of moment mi as being equal to, from that m array, it's going to be the value at index. Okay. Let's calculate the average value, just the average of those two. So m underscore avg, and that's going to be equal to 0.5 times the two added together. All right. Now we can go ahead and calculate theta I. So remember, theta I minus 1 we have, it was passed in, and so we can calculate theta I as being equal to whatever value of theta was passed in, so theta underscore I minus 1 plus m average over EI, don't forget to divide by EI if you want actually sensible numbers out of the end of this, times del x. Okay, so that is your integration applied. That's your trapezoidal rule applied to determine theta. Now that should be theta I. Let's keep things consistent. So that's theta I. Now we can go ahead and calculate VI, right? So when I described this in the previous lecture, I described it and explained it in a way where you step through and work out all of the values of theta, and then you work out all of the values of V deflection. But you can work them out in parallel like this if you like. So we'll say V underscore I, that should be an I, not a 1, is equal to V I minus 1 plus 0.5 times theta I plus theta I minus 1, again just the average value of theta, times del x. Okay, so that is our second integration used to calculate the deflection VI. So now let's store that data, right? So let's just say store data, all right? So in other words, we're saying rotation rotation, and the address we're overriding, or the position that we're storing our value for rotation, is at index, right, IND. And that's going to equal to theta I. So we're just overriding the relevant 0 there. And then we're going to do the same for deflection. So we'll say deflection at address IND is going to equal V underscore I. All right, excellent. We are nearly there. The only last little logic nugget that we have to implement, if you like, is we need to update those initial values, right? We need to update. So these were the values that got passed in, right? They got renamed to this and this, but now we need to update these values because we're stepping along the beam now, right? So let's update values for next loop iteration. All right, so I can now redefine, if I spell it correctly, I can redefine theta I minus 1 as being equal to whatever I just calculated theta I to be. And I can redefine V of I minus 1 to be whatever I just calculated V. Oh, here I'm talking and typing, it's not working. Whatever I just calculated V I to be. Okay, so now the next time I come through the loop iteration, or the next loop iteration, we're going to have new values for theta I minus 1 and V I minus 1. And the whole process continues again and again and again until we've gotten all the way to the end of our moment values, and we have a full storage of rotation values and deflection values, or a full record of rotation values and deflection values for every point to the right of support A. All right, now the last thing that we need to do, let me see, the last thing that we need to do, let's come back out here in line with this for loop. So when we finish in that for loop, we're down here and we're going to just return out of the bottom of this function the rotation and the deflection values. Okay, I don't think we have any typos in there. That's my famous last words. So let's try and run it. Well, we'll execute this, and it might spot some typos. It doesn't spot anything, but we'll only really know if we've got any errors in here. I don't think we have, but we'll only really know when we actually call this function. So I'm not going to call it now. In fact, the last thing I'm going to do before I wrap this video up is just put in a couple of notes, and then in the next video we're going to actually write the logic that calls this function. So for this here, I want a little note that says take account of the fact that support A might not be at the start of the beam. I think I've labored that point enough now at this stage. Then I want a little note here to just say that we are integrating moment values to get rotations. I'll say moment because it's M over EI values, right? So moment in inverted commas. And then I'll say integrate rotation values to get displacements. All right, is that it? I think that's probably enough notes. So there you have it. That's the function. Now, we're not doing anything yet, right? All we've done is define the function. What we're doing in the next lecture, as I say, is we're going to write the logic that's going to call this function. It's going to test the value of deflection at support B. And if that is, if there's an error, right, if it's not 0 or if it's not close enough to 0, we're going to change our initial rotation and call this function again. And we're going to rinse and repeat that again and again and again until we get a value of deflection at support B that is close enough to 0 that we're satisfied. All right, so we'll pick it up in the next video.